What's the formula for potential energy? All right, the one associated with a generalized gravitational force. Now this is one that I did not derive, I just sort of threw it up on the board when we were talking about the force, the potential energy formulas. It would have been the same time I introduced the 1/2 k delta x squared. That is if the acceleration of gravity is relatively constant, which it's not here. That's specifically, if we were talking about weight more specific, then that was the one that you would use.
Negative GM1 M2 over R.
That's the one. It is not a formula I expect you to have memorized, but just recall. See, this would, I got a bunch of masses here. So this mass right here for the kinetic energy, this is the mass of the object. I'm gonna just look, just a little O there for object. So this would be big G, mass of the object, mass of planet X over R initial, not squared, equals, and then the same thing but final. M not the final squared, plus negative big G, mass of the object, mass of the planet over R final. So conservation of energy. What can we get rid of?
Half mass of object.
Half mass of object?
Right.
Did you say half?
Half and the mass of object. Right?
All right, so if we get rid of the half, we have to multiply everything by 2, so this would have a 2 show up in front of it. That's with the other one. So let's just go ahead and do that. We're gonna multiply everything by 2 over the mass of the object to get rid of m sub o, because every term has m sub o as a factor. So we end up with vi squared minus big G minus 2 big G mass of x over R initial equals the F squared minus 2 mx over R F. Oh, I've lost my G. 2 big G. Dramatic pause for people to catch up and ask questions about what happened there. Jason?
No R squared?
No, this is potential energy formula,
Okay.
so
Different.
the square goes away. Just make that clear. Subscript I. All right. So we got rid of some of that stuff. We can still get rid of some things. Any of these equal to 0? The answer is yes. All right, let's think about our variables here. I have basically the speed and the distance are the two variables. I'm assuming the mass of planet X is not changing noticeably. Big G is supposed to be a constant. So we're left with VI, VF, RI, RF. Are any of those 0? Sorry, reword that. So I have 4 terms here. Which of the 4 terms are 0? Or, from a physics point of view, close enough.
Mass of the planet,
It's close to 0.
or no?
That, yeah, that would be a bit too much.
About R initial.
R initial?
Yeah, the distance and the distance.
What is the R? This is the same R that was on the bottom of,
Radius, right?
pardon?
Radius.
Of,
I thought it was center of the mass.
yeah, center to center distance. So then this R initial would be the radius of the planet. So we could, instead of putting R sub I there, that's gonna be equal to the radius of whatever planet X is. So that's not zero.
The initial speed.
No, that's actually what we're trying to find. Because if the initial speed were zero, it's not leaving the planet. We are picking this up after it has been launched. Well, we've eliminated two things already. Write down, this is what we want to find.
Then it'd have to be the final, right?
Yeah, as we launch it, after it has left the surface of the Earth, it starts out at some big speed. What do you know it's going to do besides move farther away?
Stop.
Or before it stops?
Slow down.
Yeah, it's going to slow down. So we want this thing never to return. So officially it's never going to stop, but it is going to get slower and slower as it goes. Now, the farther away it is, it's going to slow down at a lesser rate. It'll slow down about 9.8 meters per second squared to start with, or meters per second every second to start with, but eventually that acceleration is going to get smaller and smaller. But it is slowing down. So if we want that minimum speed to launch it so that it never returns, this is going to get really tiny. Never hit zero exactly, but this is going to be close enough to zero. Because the final speed is approximately 0 meters per second. What's happening to the distance? Well,
Increasing.
yeah. So I got a fraction right here, where my numerator is not going to change, despite some rumors to the contrary. Mass of the planet's not changing. Big G, again, a constant. 2 better be a constant. This is the one thing that's changing. So if my fraction here, I've got a denominator that's getting bigger and bigger and bigger, what's happening to the fraction?
It's getting smaller.
Smaller, smaller.
So as RF, since this thing's never returning, since RF is in essence infinite distance away, this goes to 0 because RF goes to infinity. So the fraction, so therefore 2gm over r goes to 0. That's supposed to be the infinity symbol. For the math purists, this is horrible notation. For the physics purists, it's perfectly fine. So we have taken what started out as a more complex formula, and it has now been reduced to my initial speed squared minus 2g mass of the planet over the radius of the planet, which is equal to 0. In other words, the initial speed squared is equal to 2 times big G mass of the planet over that distance. My memory says that I said squared and I shouldn't have been. I wrote it correctly. I might have said it wrong. Oh, there's the square. I did say that part correctly. So VI, so my initial speed, in order to launch this thing so it never returns, assuming it doesn't hit anything, is going to be the square root of this 2 big G mass of x over the radius of the planet. All right. As with most derivations, it's primarily just to show you that it comes from somewhere. Let's plug and chug. Let's figure out what it is for Earth. So this speed to launch something from Earth, the square root of 2 times everyone's favorite constant, 6.67 times 10 to the negative 11th, times my mass of the Earth, 5.98 times 10 to the 24th, over the radius of the Earth, 6.38 times 10 to the 6th. So if you just take the square root of the first thing Robert said last time, and I remember approximately what the answer is, so at least I have some idea if we're close or not. Okay, I knew it was 11,000 something. 11,181.93.
0.966. 966.
Units?
Meters per second.
Yes. It's a speed. All right, so this number here, 11,181, et cetera, 82 meters per second, is known as the escape speed. If I get something pointing away from Earth going that fast, it will leave and never return. And there are some things that do that. Because if you look in the thermosphere, you have these gas bits of air floating around there. You have radiation coming in from the sun. Radiation can hit some of those if they're going in the right direction or in a particular direction. You can hit those speeds and it will never return. Now, for something that is much more visible, have we ever hit that before? Remember that rockets, like the Apollos and so forth, they have boosters along the way. They're not just launched at the beginning and then slow down for the rest of the time. They're constantly firing boosters, so they have force being applied as they go. There is one case where there might have been a man-made object that did launch that. We don't know exactly how fast it was going because it was in frame and then it was out of frame. So they could come up with a minimum speed, but they were doing I believe an underground atomic bomb test. There was a manhole cover and it just basically shot up. So because it was not high-speed film, or at least for the time, they might not have had the capability of doing that. We don't know exactly how fast it is, but it did seem to get shot off and was never seen again. Did it land somewhere else in the middle of the desert? I would be disappointed if it did. All right, any questions on this? Because I was promising black holes and this is not a black hole. Feel the excitement for the black holes. All right, so we're gonna start with this part right here. If you plugged into this formula, you could play around with different mass planets, different size planets. You could come up with pretty much anything you want, except it would fall apart if there's a maximum speed. And it turns out, based upon first theory and then experiment, there does seem to be a maximum speed. And that is known as the speed of light. Now the theory predicts that anything that's traveling slower than the speed of light can never get up to it. You can get closer and closer, but you never actually hit it. Or if something starts out faster than the speed of light, it can never actually come below it. It'll never hit it either. It's a barrier either way. Now the stuff that travels faster than the speed of light, theorists have come up with a particle, the tachyon, which supposedly does this, but we have no way of testing it. So we're going to talk about things that are starting out slower than the speed of light. I'm going to take that formula and I'm going to manipulate it a little bit, because I want to solve for R. And if you recall, I can turn anything into a fraction just by sticking it over 1. I have now 2 fractions equal to each other, and now I can move stuff across the diagonal. So I'm basically gonna flip my distance, my radius of the planet, and my speed squared. So my radius, x, is equal to 2g times the mass of the planet over. Since I'm looking for black holes here, my maximum speed is c, so c squared. So how big does the Earth need to be in order to become a black hole, assuming it doesn't lose any mass? So I have 2 times 6.67 times 10 to the negative 11th times the mass of the Earth, 5.98 times 10 to the 24th, divided by the speed of light squared, which is about 3 times 10 to the 8th meters per second squared. If someone would be kind enough to calculate that. And as a side note, there is an exact number for the speed of light. We defined the meter based upon the speed of light.
Is it supposed to be a small number?
Yeah, how small did you get?
0.0088.
So that sounds familiar. 0.00886.
86. And
What would the units be?
Meters per second. No.
The distance.
Meters.
Meters. So, put that in some different perspective. So, let's see, you got one there. So that's the radius. So the diameter would be 1.66 around there. So if the Earth could shrink down to the size between my 2 fingernails there, it would be a black hole. Because the escape speed, how fast you need to go in order to leave and never return, cannot be hit. You can't get it to the speed of light. Questions here? Yes, Anaya.
So from that equation, where did you get c squared?
This is the escape speed, and so we're looking at the extreme. We're saying, all right, if the speed of light is a limit, why don't we stick that in there and see what the size it needs to be? Now, finding the speed of light, it was tricky. Galileo tried to find the speed of light by setting up 2 people on hills that are a known distance apart with lanterns. And one person would flash the lantern, the other person would see it, flash it back, and then they would time how long it took. Then they'd go to an even farther distance apart, do the exact same thing. If you figure out the reaction, if you assume the reaction time is constant, then you should be able to calculate the speed of light. And Galileo came upon the conclusion that the speed of light was, if not instantaneous, it was very, very fast. So they would take more sophisticated equipment, and eventually they got to, here we go. They came up with this idea of, if I take a wheel, I'm not gonna do it all the way around, with these cogs in it, or spokes, not a cog, what is it? Those things that stick, whatever they're called. If you shine a light through there, if you start turning and it hits a mirror and then bounces back. If this isn't moving at all, the light will hit the far mirror, come back, and you'll see it. If you start to spin this, at some point the light's gonna get blocked out, because this right here is going to basically block out the light that was bouncing back. If you spin it even faster, eventually it's gonna appear as bright as it did the first time, because it's gonna show up again basically on the next cog. As this moves to here, it'll show up in the next gap. And they came up with a pretty decent idea, and then there are variations of a theme, eventually working out the speed of light was somewhere around 300 million meters a second. If memory serves me correctly, and I don't know why I would think that, about 186,000 miles per second. All right, so now, let's take our sun. How small does our sun need to be in order to become a black hole? And then we'll talk about how realistic is it that our sun would become a black hole. So using the same type of formula here, the only difference is the mass of the sun is different, so that's the number that's going to change. So if we're talking this radius of our sun, 2 times 6.67 times 10 to the negative 11th times 1.99 times 10 to the 30th kilograms, that's the mass of our sun, divided by the speed of light squared. Oh, and that's 3 times 10 to the 8th. Squared. I am assuming our sun has the same mass. And I'll talk about the realism of that in a moment.